Okay, let us restart, right? Because there was some glitch, so let us restart. So what I was saying is that in the last lecture, or last two lecture rather, we talked about energy-based model. And in the last lecture in particular, we saw how to train energy-based model, and that was using contrastive divergence. The main challenge is in energy-based model was training and is also sampling, both because you cannot evaluate the partition function, the normalizing constant. Now, during training, you address it using contrastive divergence. During sampling, there is no such trick. You have to use some sampling algorithm. And in that context, we started discussing about Markov chain Monte Carlo. But to be very honest, we neither completed Markov chain nor could we start discussing Monte Carlo in the last lecture. So the idea for today is to talk about and hopefully complete majority of Markov chain Monte Carlo and Metropolis algorithm. Okay. So now with that background, let us start. Uh, so we will talk about Markov chain Monte Carlo, which is a short form, which we will refer to as MCMC, right? Now remember that what was the motivation for Markov chain Monte Carlo? The story that I talked about. To use law of large number with non-IID samples. Generally, law of large number is applicable with IID samples. We want to use law of large number with non-IID samples because in practice, non-IID samples is what we will often get. Think about climate data when you collect it, it's non-IID, it's dependent, right? And so on and so forth. So that is the idea. And in that context, I'll not repeat much of it, but I will just like to repeat two things that we discussed. One was the transition diagram. The other one was the transition matrix. These are the two things that we discussed and we stopped there. So what is a transition diagram? So if you remember, we said that a transition diagram, potential transition diagram will look something like this. S1, S2, S3, S4. Remind me, what were these S? These are the states that you observe at each time instant. For example, it can be weather. It's cold, mildly cold, pleasant, hot, very hot. So that is the scenario, then it should be S1, S2, S3, S4, S5 in that sense. And now the same thing you can observe each day, let's say, or each hour, whatever you like, each minute, but each day is probably better. You can observe the same thing each day. So that means these state variables will change. Today it may be very hot, tomorrow it may be rainy, mild, whatever you call it. Next day again, it might be again hot. And that's how it transition, right? And that is known as the trans states. These are the states. Transition diagram tells you or represents thematically the probability of transitioning from one state to another. The probability of transitioning from one state to another in time, in one step, right? For example, let us say S1 is um, the temperature today is hot. Then if I'm drawing something like this, let's see, and I'm giving it a probability of, let's say, 0.3. This means that given that today it is hot, tomorrow it will also be hot. That probability is 0.3. That is what this arrow means. Similarly, you can say that given that today it is hot, tomorrow it will be very hot. Let's say S2 is very hot. That probability is, let's say, 0.25. Okay. Given that today it is hot, tomorrow it will be, let's say, the mild. That probability is what is the difference? 0.55. So let's say 0.45. Okay. And given that today it is hot, tomorrow it will never be cold. I mean, let's I mean, I'm making these things up obviously, but that is to explain what these arrows mean. Similarly, from S2, S3 and S4 I can also draw. So let's say, so now I'll not give any physical meaning, but let's say from S2 to S3, this is, I don't know, 0.5, S2 to S4, this is 0.4, S2 to S1, this is 0.1. S3 to S4 is 0.1, S3 to S1 is 0.9, and there is nothing else. S4 to S2 is 0.6, S2 to S3 is 0.3, and S4 to S4 is, let's say, 0.1. So something like this, right? I mean, this is some random numbers I have written, but random number that has some pattern. For example, the summations would be equal to 1 in each case. And this is a typical transition diagram that you can potentially encounter. If some arrow is missing, that means that transition is probability is 0, right? Now, this is useful for understanding, not at all useful for writing codes. For writing codes, doing mathematics, what you will use is transition matrix. And transition matrix is a K cross K matrix, where K is the number of states. So in this case, it will be a 4 cross 4 matrix, right? So, and you can denote it using many things. I will denote it using P. So P for me is my transition matrix. So the rows represent where you are. The column represents where you are going. So what will be the first entry in this matrix? Can you tell me? 0.3, because it is 1 to 1, that arrow is 0.3. What will be the second entry? 0.25, right? Third entry? 0.45. Fourth entry? Does not exist. Then S2, if I go to S2, then 0.1. Then S2 to S2 does not exist, so 0. S2 to S3 is 0.5, and whatever is remaining, right, 0.4. Then your S3, so S3 to S1 is 0.9, S3 to S2 is 0, S3 to S3 is 0, S3 to S4 is 0.1. Then lastly, S4 to S1 is 0, S4 to S2 is 0.6, this is 0.1, no, 0.3 and 0.1. So for the same time transition diagram, this is your transition matrix, right? Where if I take one element, and let's call that element as what? Pij maybe. Let's say I take Pij. What does it mean? It means probability of transitioning from Si to Sj. This is what it means. So this basically means probability that you will be a Sp is equal to Sj given Sp minus 1 is equal to Si. So the second one is where you are going. The first one is where you are. Clear? Time? No. No. Because then it is not useful. If it keeps on changing, then you cannot predict the future. So the idea is that these are same, right? So they will not change with time in this setup. Okay. Correct. So in that case, you should not use Si given Sj. You should use Si given Sj, comma Sk. So maybe you are looking at previous 2 or previous 3, previous 4, previous 10. Those are also possible. This is the basic, most basic one. This you will see. We will call it first order Markovian. It is second order, third order, fourth order, nth order. Okay. So in that sense. Okay. Okay. So this is the transition matrix. Now, with this transition matrix, suppose at t is equal to t naught, the probability of the state variables, right, is pi naught. So let's assume suppose pi naught is equal to pi 1, maybe I should write pi naught 1, pi naught 2, pi naught 3, pi naught 4 transpose represents the probability of states at t is equal to t naught. Okay. So these are representing the probability of states. There are 4 because in my example there are 4 states x1, s2, s3, s4. So pi 0, 1 is representing probability of s1 that you will observe probability s1 at time t naught. Pi naught 2 is representing you will observe s2 at t naught, and so on and so forth. And let's call it, and that is the transpose of that, right? So now given P is our transition matrix, pi of 1 will be equal to pi naught transpose times P. Okay, and we'll see how it is coming. I'm just giving you the final answer, but we'll see actually how it comes, whether it is making sense or it is just something bogus thing I wrote. We'll see that. Okay. But what I'm saying is that with this transition matrix, if you know the initial probability of the states, you can use this to find out the probability of the states at the next time step, right? That's what I'm saying. So let us take one example within this setup and see if it is making sense or not. So tell me, you tell me, what is pi 1, 2? If I have to find out pi 1, 2, how will I find it out? First of all, what is pi 1, 2? No, the bottom one is the t equal to 1. So at t equal to 1, what is the probability of this that you will observe state 2, right? That's what it means. So how will you find it out? T up to the, no, up for state 2. You will not, the others does not matter, right? So the idea is very simple. You are exactly correct. So what you will do is that there are 4 possibilities, right? At t equal to 0, it might have been at s1. In that case, I should look at that probability multiplied by what is the probability it will go from s1 to s2, plus it might be at 2 multiplied by 2 to 2, plus it might be at 3 multiplied by 3 to 2, plus it might be at 4 multiplied by 4 to 2. The simple theorem of total probability or the sum and product law in Xn. So this is equal to pi 0 1 multiplied by p 1 2 plus pi 0 2 p 2 2 plus pi 0 3 p 3 3 plus pi 0 4 p not 3 3, right, 3 2, yeah, 4 2. This is what it should be. Everyone follows this? It's simple. Specifically, if you keep in mind that this p is nothing but conditional probability, then it is pretty simple, right? Right? Okay. So this you follow, right? So if this is what you follow, let us write the above vector notation into an expanded form, and let us see how it looks. So let us write this in vector form. So if I write it in vector form, how will it look? Pi 0 1, pi 0 2, pi 0 3, pi 0 4. This is my transpose multiplied by, see, the first one, I mean, I can write the total. Let me write the total. P11, P12, P13, P14, P21, P22, P23, P24, and I'm not writing the other two, but you know. So now you see, if you do a multiplication, that's exactly what is happening. Look, do a vector matrix multiplication, the second one you will see you will be getting what I wrote earlier, what you know, what all of us know, right? So this makes sense, and this is actually very trivial actually, that's why I did not even prove it, because this is basically the theorem of total probability in action over multiple things together, so it's in a matrix vector kind of notation, right? So now, if you follow this, can you tell me what will be, can you tell me what will be pi n transpose? Pi n transpose is what? If I take n such steps, one step was pi 0 to pi 1, second step will be pi 1 to pi 2, pi 2 to pi 3, dot 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 pi n. So now I want to represent this pi n. So after n such steps, what will be pi? How will you represent it? Repeat. Pi n minus 1, and then I want it in terms of pi 0. Correct. It is pi n minus 1 transpose times p, which is equal to pi n minus 2 transpose times p, so that is p square. So like that, if you do, you will get pi naught transpose p to the power n. P to the power n means it will not do a power n, it will multiply that p matrix n number of times. So this is equal to pi 0 transpose p to the power n, right? And like that, you can keep on transitioning. Let me know if everything is clear until this point or not, because this point onwards, the Markov chain starts. Till now, I was not even discussing Markov chain. I was just discussing some basic concepts of probability and some terminologies. Now the Markov chain will come. So if this is not clear, you will not be able to follow what is Markov chain. So let me know if this is clear or not. This is clear? Okay. So if this is clear, so here is the catch, right? If there is a P, if we can design a P or find a P for which pi n minus 1 is equal to pi n, that means the distribution is exactly the same, not even the same family or something, exactly the same. So if we can find a P such that pi n minus 1 is equal to pi n, then this means that in time the distribution has stopped changing. Now, what do you call something what something that does not change with time? Stationary. So that will be known as stationary distribution. So if you can find a p for which pi does not change, then that is a stationary condition. This will not happen for just any p. There are some p's for which only this will happen, and you need to design those, and we'll see how to design, or at least we'll see one example of such a p. Okay. So in that case, that is known as a stationary distribution. Okay. Now, if I have a stationary distribution, and if I keep on sampling from this chain, this is like a chain, right? S1, X1, X2, X3, X4. This is like a chain. So if I keep on sampling from it, given that P gives rise to that stationarity condition, then what will happen? At each time, I will sample from the same distribution. Correct? I am sampling from what? I am sampling from some conditional distribution. So it's a dependent distribution. I'm sampling from a conditional distribution, but ending up with sample from the same distribution, which means these conditional samples that I'm getting are actually from the same stationary distribution, and this is the basic concept of Markov chain. That if you can find a transition matrix that gives rise to stationary distribution, then you can keep on sampling that chain, and because of the stationarity condition, you will always sample from the same distribution. So those samples are from the same distribution, and so you can now use them for your law of largest. This is the basic principle of Markov chain. Let me write it down. So first let me draw actually. So the Markov chain will look something like this. X0, this is your variable at t0. X1. Did you notice something? When I was writing S, I was using a square bracket, right? But when I'm writing X, I'm using a circle, not square bracket, I'm square box. Why is it so? Because these are variables, those are states. States are represented using boxes. Variables are represented using nodes, which are circles. These are standard notations. So that was done intentionally. Okay. So X0 means the variable at time t is not, right? So, and in our case, this looks like this, right? This is what we have created. Correct? And this is known as the Markov chain. This is my Markov chain. Okay. This is also the first order Markovian assumption, which means xn is only dependent on xn minus 1. Or rather, given that you have observed x minus n minus 1, xn is conditionally independent of everything what happened before that. Conditional independence, remember? That statement. So this is a Markov chain, a first order Markov chain. But you can have a second order, third order, fourth order. The cost will grow in powers. So not a good idea from a practical point of view, but you can. If you really want, you can. I have never seen much of an application of that in practice, but there might be. I mean, I don't know everything, right? So there might be. Now, in our case, remember that in all of this case, in X0 also you are observing S1, S2, S3, S4 with certain probability. Here also you are observing S1, S2, S3, S4 with certain probability, and that probability was pi naught. This was pi 1, and here if you write the same thing, that was my pi n. And these were connected using the transition matrix P. The diagram is clear? You can relate it with the derivation we did, right? You can follow the derivation, right? And relate it with this one. Any doubt? Higher order means there will be an arrow. Let's say I'm using a second order. Then right now x2 has only an arrow from x1. In that case, it will also have an arrow from x0. Not all. Second order means 2. Third order means 3 order. And in that case, instead of a matrix, we will order with work with a tensor. Because right now it's a matrix because you have observed the previous one. So k cross k. But there you don't use transition matrix, right? There is no concept of transition matrix in that case. I mean, those are Markovian assumption. Those are Markovian assumption. Higher order, yes, in many cases. But those are not Markov chain. Markovian assumption and Markov chain are different things. Those are Markovian assumption, but not Markov chain. Markov chain will have states, will have probability of transition and all of those. And those are missing. So those are not, those are Markovian assumption, but not Markov chain. Okay. And you can imagine that in case of first order, my transition matrix dimension is k cross k. For second order, it will be k cross k cross k, because it will become a 3D matrix. And then you can imagine that it is growing as a power of k. So that's why I said it grows as a power of k, which means it's pretty expensive. You cannot go beyond, let's say, 3 or 4 order. Okay. Any question? No. Yeah. Right now, yes. Always, yeah. Pi is the marginal. No, not necessary. Not, it will not happen for any p. You have to first find a p that will result in stationary. Not any p will not result in stationary distribution. It has to be a p that is designed by you. Not just any p will give you stationary. Right? So no. Okay. So now what I was saying is that if for a given p, pi n is equal to pi n plus 1 is equal to pi n plus 2 is equal to some pi, let's say, then we call it, what is the name? Those who have done uncertainty codes would be able to tell what is this property. Stationary happens, but it gives rise to the stationarity condition. That's correct, but it has a very specific name. Pi invariance. This property is known as pi invariance. Okay, so this is known as pi invariance. That means you have a kernel that is invariant to the pi, right? This again for a given p. It will not happen for all p. So this is known as the pi invariant property or pi invariance. Clear? And the idea is that if we can design a p that is pi invariance, we can sample from this chain that you see at the top, and that will give samples from the same pi, which is my target distribution. That is the idea of Markov chain Monte Carlo. Okay. It is clear what is the stationarity in this case, what is pi invariance, and is it clear that it does not happen for just any p, you need to design that p. These are the three things that should be very clear to you. And lastly, pi invariance is a necessary condition but not a sufficient condition. There are additional conditions, I'll come to that. Okay. So, okay, maybe I can ask this question, right? So I am stating this fact. Pi invariance is a necessary condition for the Markov chain Monte Carlo, but is not a sufficient condition. Can you give me one example where this will happen? In cyclic process, how will be pi n plus 1 will be equal to pi n plus 2? You have to first give me a scenario where pi n plus 1 will become equal to pi n plus 2. And then still you know that that's not a correct way of sampling. The easiest way is if p equal to 1 diagonal identity matrix. If p equal to identity, it will always be pi n plus 1 is equal to pi n plus 2, right? It's a given thing. But that means you are always sampling from the same state, which means you are not going to all the states, which means those samples are useless. Where you will start, you will get stuck there. You will, right? So this property is known as, this means your Markov chain is reducible. So the property you need is irreducibility. The other one you were saying, we'll come to that later. The other one you were saying was correct, but I'll come to that later. But you could not explain it in this context. Okay, that is also aperiodicity was also correct. We'll come to that later. Now, okay, but this is all for discrete, and we care for continuous, mostly, at least. At least if the course name is probabilistic machine learning for mechanics, then it's continuous, right? At least that's where at least the mechanics is. Okay. So in mechanics, it is rarely you will see something discrete. So what will happen to, let's say, this equation, pi 1 transpose equal to pi naught transpose time p in case of continuous. So let us write it down. For continuous variables p, and p is PDF now, keep in mind, okay, x n plus 1 will be equal to integration p x n k x n comma x n plus 1 d x n. You follow this? You will follow this if I go and write it down here, that k of this is equal to probability of x n plus 1 given x n. Now you should follow it, right? I mean, it's the conditional, and you know that by the definition of transition. So here P is PDF, I already told you that. K is my transition kernel. So matrix, when you generalize to infinite dimension, becomes kernel. Vector, when you generalize to infinite dimension, becomes function. Okay. So if you take a vector and make it infinite dimensional, that's the function. I mean, not a formal definition, but that's how it is, right? And matrix, that becomes kernel. It basically tells you how close or far 2 points are in general, but in this case, it is a transition kernel. And this is exactly same actually. This violet one, that's the sum rule law, right? So instead of summation, I have written integration. I have not changed anything else, right? So this is what you will get in case of continuous. And now if Pxn is equal to Pxn plus 1, then K is a transition kernel that is pi invariant. If for a given K, P of xn is equal to Pxn plus 1 is equal to Pxn plus 2 and so on and so forth, then K satisfies the pi invariant condition. Correct? So if for a given K, okay, I should write it like this, dot, comma, dot, because it will be xn, xn plus 1, xn plus 1, xn plus 2 and all of those things. P xn is equal to P xn plus 1 is equal to P xn plus 2, then K is pi invariant Same thing from before, nothing new. Clear? Okay. So if this is clear, so now let us take a step back and remind ourselves, where did we start? What was our objective? To sample from an unnormalized distribution. Correct? That is our objective. We should not lose sight of our objective. Our objective is to sample from an unnormalized distribution. Right? Okay. Now we are also saying that we can sample from any distribution. There is nothing unnormalized here. We can sample from any chain. We can sample using Markov chain Monte Carlo if you can design a kernel K that is pi invariant at the very that's a necessary condition. Right? So next, let us do two things. First, as I said, there are two additional conditions, so let us discuss that. And then let us go directly into the Metropolis algorithm and let us look into how you sample using Metropolis algorithm. And then from Metropolis algorithm, we'll come back and see that how does it satisfy these three conditions: pi invariance, irreducibility, aperiodicity, and so on and so forth. Okay. So first of all, pi invariance is a necessary but not a sufficient condition. Pi invariance is a necessary but not region, not sufficient condition. I think either mouse, if it is inside, or if it is outside, then pigeon. These are the two possibilities of this sound. Okay. So pi invariance is a necessary but not sufficient condition. We have two additional conditions. Uh, we should also ensure irreducibility and aperiodicity. Can someone close that door? It's okay. We should also satisfy irreducibility and aperiodicity. Thank you. What is irreducibility? Irreducibility means starting from any state, you should be able to go to any other state with a finite probability. No matter where I start from this room, I should be able to go to each and every corner of this room with some finite probability. If this can be satisfied, then we call it irreducible. If not, then we call it as a reducible chain, which means once you go somewhere, you cannot escape, you get stuck, or at least you cannot go to all other points. Anything is possible. It need not be direct. Okay. So for example, let me draw two transition diagram. Okay, two transition diagram, and you tell me whether, in your opinion, that is reducible or irreducible. Okay. So let's say, okay, let me define it first actually before I draw. This I said was should be able to go to any state no matter where we start with finite probability. Okay. And now let me draw two diagrams. And let us take that same example of 4 states. Okay, S1, S2, S3, S4. And let me draw something like this. What do you think? This is a reducible or a irreducible one? Hmm? Why? Hmm? How many things? How many things it is irreducible? And how many things it is reducible? Reducible? Why? S4, if you go there, you are stuck, right? So let us do one more thing. Now, it is reducible, irreducible. Now, you understand, right? Starting from any state, it should be able to go to any other state. That's the only criteria. Okay? Because it is reducing to some state. That means you are only getting one type of samples. One of the mode is getting eliminated. So the original chain was like 4 states. It is getting reduced to 1 or 2 states. So in the original diagram, it was getting reduced to S4 at some stage. At some stage, it will reach S4. And once it goes to S4, it will stay in S4. So that means the chain which was having 4 states has been reduced to 1 state. Uh, if it is really, yeah. No, this is not a property of Markov chain. This is a property of Markov chain Monte Carlo, right? Not a property of Markov chain. Okay. I mean, it can still be a Markov chain, but I mean, as I said, autoregressive model is a Markov chain, but it's not Markov chain Monte Carlo. There is no concept of transition probability. Markovian assumption is there in that sense. Right? Clear? Irreducibility. Uh, but how will you ensure irreducibility in case of continuous? This was discrete and easy to follow. Think about continuous. Now, let's say my transition kernel is uniform. Let's assume that it is irreducible or reducible. Hmm? Reducible? Why? Depends. You are right actually, but it depends. If your original distribution is bounded and the uniform is having the same bound, then it's okay. But if the original distribution is like say Gaussian, which can be from minus infinite to plus infinite, and then this is from A to B, then it's reducible because you can never explore the area beyond B or before A. Right? So it will depend on what kernel you are selecting in that sense. Okay? And whether it is reducible or irreducible will depend on the original target distribution. In this case also it depends on the original state. So in that sense, right? So, okay. Clear what happens in continuous case? The second condition is aperiodicity. Why is aperiodicity important? Aperiodicity means non-periodic. Why is it important that it should be non-periodic? Correct. If it is periodic, then it is not random. Then what does it even mean by law of large number? Law of large number is for random samples. It is not for periodic samples, right? So that is kind of intuitive, right? Clear? So these are the two conditions. Now we have all the three conditions that we need to design a kernel. Given a distribution pi, we'll try to design a kernel K such that it is pi invariant, it is irreducible, and it is aperiodic. So it sounds good on paper, right? It is very difficult in practice. it's extremely difficult to design a kernel, almost impossible to design a kernel that is pi invariant. You cannot design a kernel that is pi invariant directly. So for that, what we did was, or what I not, or not we, what researchers did, what those who developed this did was, they came up with the idea of detailed balance. They said that, okay, we will not satisfy pi invariance, we will satisfy the detailed balance condition, and detailed balance happens to be a more stricter condition. If something satisfies the detailed balance, it automatically satisfies the pi invariance. But the opposite is not true. We will take a detailed balance condition and try to design kernel following the detailed balance condition. And that automatically will mean that it will be pi invariant. We will also ensure aperiodicity and irreducibility. And using that, we will now design the kernel. So instead of pi invariance, we will use what is known as detailed balance. What? In continuous, we are never calculating the probability. We are calculating the PDF. PDF is not probability. That was the first thing I talked in the lecture. Integration, even then it is PDF. Because P of x is PDF, P of x given y is PDF. So Px multiplied by P of y given x gives you P of x comma y. That's a PDF. Integrate over y, that gives you PDF. No, that's not probability. So it's not probability. Okay. Okay. So what I was saying is satisfying pi invariance is non-trivial. So we use an alternative criteria which guarantees pi invariance, and I will prove that, known as detailed balance. Okay, and this detailed balance takes the following form: pi of xt k xt 2x t plus 1 will be equal to pi of x t plus 1 k x t plus 1 comma xt. Okay, this is known as the detailed balance condition. You take the probability at current state, multiplied with by it transitioning from current state to the next state, or yeah, state at next time instant, I should say. That should be equal to the probability of being in the next state multiplied by probability of transitioning from the next to previous, xt plus 1 to xt. And if these two are same, then we call it detailed balance. Detailed balance because this way and this way, that is balanced. So detailed balance. Okay. Now, can you prove that this satisfying this automatically means satisfying the pi invariance? It's trivial to prove. Okay, let us see. It will be proved in the space remaining. So pi invariance is what? Integration of pi xt k. This is the left hand side of right hand side of detailed balance, right? Right? Not detailed balance, sorry. This is the pi invariance. Now, if I substitute the detailed balance equation, what happens inside the integral? Pi xt will become pi xt plus 1 and k x This will become xt plus 1 comma xt d of xt. Right? Everyone follows? Phi of xt plus 1 is not a function of xt. It will come outside the integral. And what happens to the remaining term? Why 1? I know it's 1. Pi x t plus 1 integration k x t plus 1 comma x t d of x t. Now someone said that this integral is equal to 1. Why is it 1? Because, I mean, all of you are correct, but one thing you have to specify, because without that it will not be, because it's a distribution over xt. It's a conditional distribution over xt and you are integrating over xt, right? If it was xt plus 1 given xt, then it would have not been 1, because the integration was not over xt plus 1. Then it would have been a constant and should have come outside. So it is 1 because by definition this transition kernel is probability of xt given xt plus 1. So the distribution is over xt and I am integrating over xt. That's why it is happening. If it was opposite, then it would have not happened. I mean, the integration and the random variables would be same for it to be equal to 1. Obviously, I mean, very minute thing, but very easy to miss. Right? It means that the same thing. What is the interpretation of transition probability? Given that you are in xt plus 1, what is the probability will go to xt in one step, right? The same thing. What was Pij? Given that you are in state Si, what is the probability of you going to state Ij? That's what it is, right? Same thing. Nothing changes. Yeah. Simple. This, for a PDF to be equal to 1, it has to be integrated over the same variable, that is the PDF for which you are considering. So integration of fx dx is equal to 1. Integration of fx dy is not equal to 1. That is equal to probably 0 or fy or something like that. Fa is equal to fx, right? For integration of fx dx is 1 because you are integrating over the random variable, right? In this case, the integration is over random variable xt and that's the PDF is over. But if you write probability of xt plus 1 given xt and then the integration is over dxt, that actually makes no sense. That should not be equal to 1. That's all. I mean, it's very simple actually. Too trivial actually, but yeah, you were saying. They are random variables, but xt plus 1 becomes a sample, obviously. Whatever you condition on is considered to be deterministic, right? So xt plus 1, when you are conditioning on, it's some value of xt plus 1. And for that value, you are looking at the distribution of xt. You define it. Why not? Simple. You have p of xt given xt plus 1 given xt, right? You know that. You can draw a sample from that. Condition on that sample. Now find out p of xt. Condition is always on sample, right? You can always define that. Okay. So basically, detailed balance is what we will satisfy. That will means that pi invariance is satisfied. Ideally, pi invariance is the bigger circle. Detailed balance is a smaller circle within this. Which means that if it is satisfying the detailed balance, it is automatically pi invariant, but does not mean everything that is pi invariant is detailed balance. It will satisfy detailed balance. Louder. Obviously, they will exist because that's the property of transition. That's the irreducible property. Obviously, why is it one? That's the property of PDF. It is one because it's a PDF. Nothing more, nothing less. It's one because it's a PDF. It has nothing, no more meaning than that. It's a PDF and you are integrating over PDF. By property of PDF, it's one. You do not need any other reason for it to be 1, right? For PDF to be 1, integrating, you don't need anything else. That's the definition of PDF. If it is not 1, then it's not a PDF. As simple as that, right? If it is not 1, then it's not a PDF. And that's the whole point of the whole definition of PDF, right? Okay. Not yet. That still needs to be satisfied. Okay. Um, okay. Any question? What? It should not. It should not have an impact. Conditional PDF is also a PDF. Any PDF, the definition is that it should be equal to 1. If the conditional starts impacting in, then there should not be anything known as conditional PDF, because it starts violating the definition of PDF. For a Gaussian, the easiest example is for a 2D Gaussian. How does the contour look like? Bell, but 2D, something like this. What is the conditional? It will look like a this PDF. You integrate in this line, you will get 1. You integrate in this line, you will get 1. You integrate the total thing, you get 1. That's the total probability table. You remember total probability table? What happens? Each row you add, you get 1. Each column you get 1. Multiply everything, you get 1. That's what it is, right? Okay. Any question? Okay. If there is no question, finally let us start the Metropolis algorithm. Clearly, I cannot cover the Metropolis testing today, but that is fine. I mean, Metropolis testing will not take much time because it is just one modification over Metropolis. So now, let us talk about Metropolis algorithm. Remember that I told it last time, but I'll repeat that the Markov chain Monte Carlo was formulated in 1907 or something like that. 1908 or 7, I forgot the exact date. Metropolis came around 1950. So although Markov chain Monte Carlo, the concept was there, this algorithm came much later. Okay, so keep that in mind. Metropolis testing came in 1971. So what I will do is as follows. I'll first write down the algorithm. Then we will discuss in that algorithm where is the transition kernel. Does it satisfy the property of transition kernel? We'll go backward. First we'll write down the algorithm, and then we will talk about the other aspects, that why it is a Markov chain Monte Carlo algorithm. Markov chain Monte Carlo is a family, right? Metropolis algorithm. Any idea for this algorithm? What is the starting point? What are the things you will need? Huh? Someone said correctly. What is it? Step size. Where is sigma? I did not even define sigma. I know you are in the IQ course, but I am not told everything about sigma. N, I have talked about N. You need to tell the number of steps, right? The length of the chain. That is N. So one thing you need is length of the chain. What happened? Length of the chain N. You also need something known as proposal distribution. This is something I'm introducing new thing. I mean, in this context. And proposal distribution we write as Q of y given x. What is y? What is x? I'll talk about later. Okay. But there is something known as proposal distribution. Okay. And correct. You need a unnormalized distribution from which you want to sample. Distribution can also be normalized, by the way. You can also use it to sample from normalized, but you can also use it to sample from unnormalized, both. So maybe let us take a normalized distribution only from which I want to sample, right? So let's call it pi of x. Okay. And then I will talk about why it will work for unnormalized also. But right now, let us take normalized. Okay. We'll also need one more thing, an initial sample. x naught. Initial sample, basically you can draw it from pi naught. You can assume any pi naught and from there you can sample it. Remember, if a distribution, if you can design a kernel that is pi invariant and irreducible and aperiodic, then it does not matter where you start from. You will converge to the stationary distribution. The only question is whether you will converge in 10 steps, 100 steps or 1000 steps. If you start from a very good pi, you will converge in maybe 10 steps. If you start from medium kind of pi, you will probably medium kind of, you will probably converge in 100 steps. Very bad, maybe 1000 steps. So you will converge, the chain will converge. The question is in how many steps it will converge. That will change, but it will converge. Because you have designed a kernel such that it is pi invariant. That is independent of your starting point. So that's why the starting point you can take on your own. You can sample from some distribution. It just does not matter in the long run. No, there is no kernel yet. There is no concept of kernel in this algorithm as such. So that will be my question after I decide that. You will tell me what is the kernel. But in the algorithm, there is no kernel. Okay, in the algorithm, there is no kernel. Okay, but you will tell me after I am done with the algorithm. I'll ask all of you actually what is the kernel. Okay, so these are the things that you start with. Okay, these are the things that you start with. Now, what you do is very simple. For n is equal to, let's write 0 to n minus 1. Okay, for n equal to 0 to n minus 1, that is n steps, right? What we will do is as follows. You will sample a y from q of y given xn. You will sample a y from the proposal distribution. This is a proposal, not the kernel. Remember, I'm repeating again and again. Okay, this is a very common confusion. People confuse that proposal is my kernel. Proposal is not your kernel. Okay, you sample this thing. Okay, so now you have two samples. Do you agree that you have two samples? What are the two samples? Y and xn, which in right at the beginning will be x naught, but you have y and x naught, two samples, right? You will compare these two samples and based on that take a decision. And this is why it is applicable to unnormalized also. When you compare, the normalizing constant just cancels out. This is the reason. What you will do is that then you will compare. What you will compare is as follow. If phi of y is greater than phi of xn, you set xn plus 1 to be equal to y, else, okay, else you will set xn plus 1 is equal to xn. Okay, this is the original concept of metropolis, but no one uses this form. So I'll come to the next form soon, because this is the incomplete metropolis algorithm. But this is more intuitive. You can understand, right? Between the two samples, whichever is having the higher frequency, I should keep that sample. That's what it means, which is intuitive. But you are not going to use it because this is not statistically complete. There is another version which I'll write now, which is statistically complete. So let us write that second version. So in the second version, so first version I've written, right? So whatever I've written here remains as it is, nothing changes. Okay. The second version I'm writing on the right hand side. but this portion will not change. This portion will change, and let us see. So what you will do is simple, you will draw one more sample U from a uniform 0 and 1. Okay? And then you will calculate something that is known as acceptance ratio. You find out acceptance ratio, and this is defined as minimum of minimum of 1 comma pi of y pi of xn. Okay? And then if a is greater than u, then you set xn plus 1 is equal to y with probability a xn comma y, which is this one, the same thing, right? Else you will set xn plus 1 is equal to xn with probability a 1 minus a xn comma y. Okay? What we did here, because it is a stochastic algorithm, not everything to be accepted. So what is getting accepted now may be rejected next time. So that's why we brought this concept of ratio, and that ratio is quite intuitive because that is exactly same as what I wrote earlier. If you take the ratio, you will see that a greater than u will automatically come, right? If you take that a y pi y divided by pi xn, that is actually your a. Yes, it can go beyond 1, and because we want it to be probability, so we take the minimum. If it goes beyond 1, then probability is 1. That is for sure we'll take it. Otherwise, we will reject it. In this case, even if it is less than 1, you can still accept it, but with a very small probability. Okay, so you give some probability to even accept when, so that gives you more scope of exploration. We are not rejecting. Look at it. Are you rejecting? When that is, we are not rejecting anything. We are retaining the previous sample, right? If we are rejecting that, we would have said that rejected. We are rejecting it, and in that case, that will become a different algorithm that is known as accept reject algorithm or rejection sampling. Correct. But we are not. We don't call it we are rejecting. We are taking the previous sample. Now, why are we taking the previous sample? Because it is very simple. Because that is more probable than the new sample. That's what the acceptance ratio means, right? That ratio, that means is very small, which means that is having a very small frequency as compared to the previous one, which means the previous one is more probable. How will you get stuck? There is a finite probability. You are forgetting. You are generating a u also, right? That u is from 0 to 1. So it is highly probable that even not highly probable. It is also probable that even if you get 0.5, that is ratio. So although it is less, still there is a 50% chance of it getting accepted. Because when you generate a uniform with 50% chance, it will be less than 0.5. Correct? Obviously, because in 0 to 1, right? Probability. So each point is equally probable, right? Always. Hmm? Hmm? Yes. Oh, that will come later. For now, we choose whatever we like. Okay. We'll decide that later. One of the good proposal can be one of your other generative models. Who knows? Train a flow-based model Whatever sample it is giving is a proposal. Who is stopping you from doing that? We don't do it in Metropolis algorithm, by the way. Metropolis algorithm is much simpler, but that's also a possibility I'm saying, right? In that case, maybe most samples will be accepted, and that's fine. Okay, any doubt? Okay, so there is no doubt. Where is the transition kernel? I said I'll ask this question. Where is the transition kernel in all of this? There has to be a transition kernel, because without that, it's not a Metropolis algorithm. It's not a Markov chain, but it is a Markov chain. So where is the transition kernel? That's acceptance ratio. That has nothing to do with kernel. Correct. Yes. So basically what you are saying is that the transition kernel can be formed using the fact that there is a queue of y given x, and given the fact we are either accepting or rejecting, right? And that is correct. But how? Let us see. What is the transition kernel for this? And this is a little bit more involved, I will say. Conceptually, it's a one-line expression, but conceptually you need to understand, so follow very closely. Okay. So our transition kernel definition is xn to xn plus 1, right? Correct? This is my transition kernel. Now tell me, in how many ways you can go from xn to xn plus 1 following this algorithm, the right hand side? Two ways. One way is that you select a y and you accept that y as a xn plus 1. The second thing is you select a y and that get rejected. So your xn plus 1 is equal to xn, and that's a way of xn plus 1 also. So there are two ways you can go from xn to xn plus 1. First way is you select a y and it gets accepted. The second way is you select a y and it gets rejected, and so xn plus 1 is equal to your xn. Everyone agrees? So accordingly, if it is accepted, then it's straightforward. So if it is accepted, then it is equal to q x. If it is accepted, then y is xn plus 1. So this is where you are sampling from. Multiplied by, there is a probability it will be accepted, it is not always accepted. Right? So this is the acceptance case. What will be the rejection case? Someone tell me. Q of y given xn multiplied by 1 minus a xn comma y. This is incomplete. I am missing something. Tell me what. Integral. You can xn plus 1 can given xn in different ways, because y might be 10 ways you are rejecting y. So it should be integral over all possible y's which can get rejected. However, in case of acceptance, it is only one, because the acceptance once, whatever is accepted becomes xn plus 1. Whereas in rejection, there might be 10, 20, 30 million ways, actually infinite ways of getting rejected, and whenever it gets rejected, you go back to the same thing. So the probabilities would be over all of those, right? I'll repeat. Whenever you are getting accepted, your y is automatically becoming xn plus 1. That is just one way, assuming xn plus 1 is constant, right? But whenever it is getting rejected, xn plus 1 is equal to xn, but xn plus 1 can become xn for different possibilities of y. All the possible y's that gets rejected will give you xn plus 1 equal to xn. So that's why the integral. Clear? This is your transition kernel. So you do not get the transition kernel directly, you use the proposal and then use the proposal to arrive at the transition kernel. Right? Now, it needs to satisfy what are the conditions it needs to satisfy? Detailed balance, then irreducibility, then aperiodicity. Let's start with aperiodicity. Can you explain why it is aperiodic? You don't need any more information for that. Because there is a, even if it is periodic, the same samples can get rejected with a finite probability. It is not guaranteed that even if you periodically arrive at the same point, maybe one time it is getting accepted, next time it is getting rejected. There is a finite probability. So that will break the periodicity. The fact that we reject with finite probability ensures that it is aperiodic. Because even if it is periodic in the worst case scenario, still that will break the periodicity. How is it irreducible? It is not irreducible. Until and unless you select a proper Q. Generally, someone was asking, right, what Q will you select? So one of the possible Q you select is Gaussian, random walk. That's the most popular one. If you select Gaussian, it is irreducible. You can get any y from minus infinite to plus infinite. It makes it irreducible. So it becomes irreducible based on your choice of the proposal. There are two reasons. One is because it is minus infinite to plus infinity. That is the main reason you take it to be Gaussian. That is the main reason why it becomes irreducible with Gaussian. But it is not compulsory for you to use Gaussian. If you know the range of the original distribution, you can use uniform in that range as proposed, or not that range, some range. Exponential is only non-negative. Exponential is not, does not go to negative, right? But it can be exponential also. But the idea of random walk is that it is Gaussian. Because random walk is like you will add a Gaussian noise. And that came from random walk came from, you know how the name random walk came, how the algorithm was came. Right? Yeah. The motivation was a drunken person that when it is walking, if it is here, it can go anywhere. It can go back also, front also. That's the idea. That given my current state, randomly I can take a step and that can be anywhere. So it's a Gaussian. So that is what random walk is. If you know that, yes. If you can make it problem specific, it will converge quickly. Okay. If it is problem specific, it will converge quickly, right? In that sense. Even with uniform, you might get, I mean, if you take a proper uniform, that might make it a irreducible one. Okay. But with Gaussian, it is guaranteed to be irreducible. That's what I mean. So I'll repeat, it is aperiodic because there is a finite probability with which you are rejecting. It is irreducible because your proposal is Gaussian. And last and most important, and yeah, the last thing, I'll do that. It will probably take 5-10 minutes and then I'll stop. How does it satisfy the detailed balance condition? Okay. So first was aperiodic. It's ensured as a sample can be rejected with finite probability. The second was irreducible. Selecting proper Q ensures irreducibility. Okay. And lastly and most importantly, detailed balance condition, which will take 1 page, 2 page, I don't know. Let us see. Detailed balance. What is the detail balance? Pi of xt k of xt to xt plus 1 is equal to, by the way, there is one more condition I forgot to mention, but I will mention it while proving this. Okay. So this is the detail balance condition. Let us take the left hand side, substitute that k, and see if we can arrive at the right hand side. So taking LHS and substituting k, what do we get? Can someone tell me? Pi of x n, I mean I was writing n, right? So let's write xn. Okay. Pi of xn, and then k is equal to what? Q of xn plus 1 given xn multiplied by a xn comma x n plus 1 plus integration q of y given xn 1 minus a xn comma y dy, right? The first term inside the bracket I will call it a n. The second term inside the bracket I will call it b n, and I will take and tackle those terms separately. So this term is my a n. This term is my b n. Okay. Which term should I start with? Which do you think is the easier one? A n or b n? Wrong, b n. Okay. It's a b n. Okay. So let's start with the second term. It is pi of xn multiplied by bn, right? Which is equal to pi of xn multiplied by integration of q of y given xn, right? Multiplied by 1 minus a xn comma y dy, right? Now what is this case representing? What is this case representing? The second term was representing what when you formulate a transition kernel? Rejection. What happens when the y sample is rejected? So xn plus 1 will be equal to what? Xn. So this represent the scenario where xn plus 1 is equal to xn, right? So I can go and put wherever there is xn as xn plus 1. I'll just put that. So this represent rejection scenario, right? Scenario, which is equivalent to xn is equal to xn plus 1. So substituting this thing. So therefore, the first term was pi of xn. I'll write pi of xn plus 1. You can understand, right, what is happening? Q of y given xn, I'll write y given xn plus 1. 1 minus a xn comma y, I will write xn plus 1 comma y dy. right? Now what is this term inside the integral? If the previous term was bn, is it not bn plus 1? So this is equal to what? Pi xn plus 1 times b n plus 1. You can see what was bn, so in that sense, right? Why? No, no. We are saying the whole condition happens, right? We are considering the whole term as a whole. Yes, you are right that the inside term holds when xn plus 1 is equal to xn. But in that case, the outside term should also become xn plus 1. Because when you evaluate it, xn plus 1 is equal to xn. So in that sense, I'm not saying that for the first term it will happen. It will not happen. But for the second term, it is bound to happen because of the scenario, right? Now let us look at the term, the more difficult one, which seems easy. So focus on the first term. But this is more interesting, to be very honest. First term is what? Pi of xn an, which is equal to pi of xn. An is equal to q of xn plus 1 given xn. And then acceptance ratio, I will write the whole form, which is minimum of 1 comma pi of xn plus 1 given pi of xn. If I write, I can write pi star and all of those things, it will not matter, right? This is the term, right? What I will do is very simple. The pi xn at the beginning, I'll push it inside the bracket of minima, right? So what will happen if I push this term inside? Minimum of pi of xn comma pi xn plus 1. The first algorithm I wrote. This is equal to q xn minimum of pi xn comma pi xn plus 1. Any idea what will I do next? Take it out. Exactly. So take pi xn plus 1 outside. Pi xn plus 1 q xn plus 1 given xn minimum of 1 pi xn by pi xn plus 1 comma 1. So I'll write the 1 first before that. You can see that everything is matching except one term, right? What is that term that is not matching, which is not reversed yet? Q. Q also needs to be reversed, right? Which has not happened, and that will not happen. In this case, you cannot reverse Q automatically. Therefore, there is an additional condition for Metropolis algorithm. Whatever proposal you use has to be symmetric. Metropolis algorithm is only valid for symmetric proposals. Symmetric means probability of or Q of y given x is equal to x given y. So Metropolis algorithm is only applicable with symmetric proposals. Okay. So let me write it down. Metropolis is only applicable with symmetric proposal, which means Q of y given xn is equal to Q of xn given y. Now, if you use this condition, we are already done, right? So, using this, finally we are there. pi of xn plus 1 q of xn given xn plus 1 a of going from xn plus 1 comma xn, which is equal to pi of x n plus 1 multiplied by a n plus 1, right? And now you combining, you know the detail, this proves the detail balance. So dv is proved. Okay. So what is the constraint on Metropolis algorithm? The proposal has to be symmetric. Metropolis Hastings algorithm addresses this concern. The only difference between Metropolis and Metropolis Hastings is that in Metropolis Hastings you can use a generalized proposal. You don't. It does not need to be symmetric. There is a small tweak that it does, and that addresses it. This is this issue, and we'll talk about it in our next lecture. Now Friday there might not be lecture. I'll let you know. There might be. I might as well take. Okay, that depends on certain conditions on my side. Okay, but the next lecture will wrap it up. We'll talk about Metropolis Hastings and then finish our discussion on energy-based models. That means if I take class on Friday, from next week we are starting with score-based model, which is then going into diffusion. Okay, thank you.